Chapter 4 is probability, and many students find this chapter to be one of the more difficult chapters out of the whole entire book. So section 4.1 is statistical and critical thinking. The first thing that we have is a few different vocab words. First one being probability. The probability of event refers to the likelihood that the event occurs. The probability of event A is represented by P and then A in parentheses because that's our event, and is greater than or equal to 0 and less than or equal to 1. Outcomes are different ways an event can occur. Our sample space of a probability experiment is a collection of all possible outcomes. Event is any collection of outcomes from a probability experiment. An event or a simple event is an outcome of an event that cannot be further broken down into simpler components. So the example right below is a simple event. It says the probability experiment consists of sampling M&M colors. Identify the outcomes of the experiment. So the different colors that we have for M&Ms are going to be red, blue, yellow, orange, brown, and green. You put commas in between each of these different outcomes that we would have, and then we're going to put some braces or curly brackets around that to symbolize that that is our set. Determine our sample space. So if you count up the number of colors that we have, it's 1, 2, 3, 4, 5, and 6 different colors. We use that n to state our sample space. So this is n is equal to 6. It says define the event not selecting red, blue, or green. So we're not selecting these for part C. So I'm going to go ahead and call this event E. And that means if it's not red, not blue, and not green, then we're left over with yellow, orange, and brown. So that's going to be our outcome. So yellow, orange, and brown. This idea is also called a complement, and we'll get into that in a moment. So notation for probabilities says let P, it's a capital P, denote probabilities. A, B, and C denote specific events, and you can use different letters than just A, B, and C, and you could also write this out in words. And then we have P and A in parentheses denote the probability of event A occurring. And again, it doesn't always have to be the letter A there. Probability model lists the possible outcomes of a probability experiment and each outcome's probability. And a couple things to note here is going to be the probability of an event is going to be greater than or equal to 0 or less than or equal to 1, any of those values that are in there. So probability of event E is the probability of event E, and it's written as a decimal or fraction. If you add up all those probabilities, it will sum to 1. So the sum of all probabilities of all outcomes is equal to 1. Then we have 3 different approaches for finding probability result values that are between 0 and 1. Number 1, relative frequency approximation of a probability. Conduct or observe a procedure and count the number of times event A occurs. And so there's a little formula that's given. And so this is probability A is the number of times A occurs divided by the number of trials of the experiment. Number 2 is the classical approach to probabilities. This requires equally likely outcomes. And if a procedure has a different simple event that are equally likely and event A occurs in S different ways, then we have the probability of A is the number of ways A occurs divided by the number of different simple events. And that formula is given there. And then we have 3, which is subjective probabilities. P of A, the probability of event A is estimated, and really quick, this is estimated by using knowledge of the relevant circumstances. So it's almost like an educated guess. The next thing that we have below this is called the law of large numbers, and this is a procedure is repeated again and again The relative frequency probabilities of an event tends to approach the actual probability. The example at the top of the next page says determine which approach is used for finding the probability and then find that probability. So part A says in a recent year, there was about 3 million skydiving jumps and 21 of them resulted in death. Find the probability of dying while making a skydiving jump. So since these values are given to us and we know them, they're counted and observed, this is going to be a relative frequency approach that we're using. And so in order to find the probability of dying while skydiving, it's going to be a skydiving death. And the total number of jumps that we have observed is 3 million. So that's going to go in the denominator. And in the numerator is the number of deaths that occurred, and that is 21. So let's divide this on our calculator and see what the result is that we get. On the calculator, we're going to do 21 divided by 3 million. And then enter. And you'll notice that your answer is 7e to the negative 6, or 7e negative 6. And this e is going to stand for times 10. So this is important to know that this is not the correct way to write your answers. And let's talk about how to correctly write those. The result that the calculator gave us was 7e negative 6. And again, that e we're not allowed to use in our results or in our answers. So the e stands for times 10. So this is the same as 7 times 10 to the negative 6. We have a decimal point that's right after 7, and that negative 6 means we need to move our decimal point 6 times to the left. So going ahead and doing this, we have 1, 2, 3, 4, 5, 6. And in each of those spaces, we would have a 0. So 5 zeros, and then a 7. For us, usually it asks you to round so many decimal places, and we'll get into that in a moment. But for right now, we'll say this answer is very small, very unlikely. So 0.000007. The next part, part B, says find the probability of rolling an even number on a fair dice. So for this, there are no numbers given to us, and also the likelihood of it landing on any of those numbers is equal, so we have equal likely outcomes. And so this is our classical probability approach. And so asking about the probability of rolling an even number and so in the denominator, how many total numbers are on a dice? It would be 6. And how many of those numbers are even? You have 2, 4, or 6, so there's 3 different numbers. This could simplify to 1/2, or you can just divide it on your calculator and get 0.5. Part C says what is the probability that the next dollar bill you spend was previously spent by Sabrina Carpenter? And so for this, there is no data. We have no information about this, no data. We don't know if you just saw her or if you've never seen her. And so we're going to make a guess. And because of this, this is our subjective probability approach. And so for the subjective probability approach, I'm going to say this answer is very unlikely for myself, so very small probability. And I am just going to say it's about 0. I'll put in a bunch of zeros here to represent that it is very unlikely, and then a 2. It is up to you for whatever number this is. Maybe you were just talking to her and there's more of a likelihood that you have spent $1 that was just spent by her, and so you might have a larger number. Or you might just have a 0 if you don't even use cash. So we have complements of an event. And a complement of event, A, is denoted with an A bar. Sometimes you'll see it with A sub C written up at the top like an exponent. And so A bar is the complement of A, and this is the outcome in which event A does not occur. So the example right below says, in recent years, there were about 3 million skydiving jumps. 21 of them resulted in death. Find the probability of the complement of the event. And the complement of the event would be not dying while making a skydiving jump. So A prime, or A bar, is going to be the number of jumps that we had, which was 3 million, minus the people that passed away. And this is giving me a number, a really large number. And this really large number represents the number of people who survived, who did not die. So the probability of not dying, again, that 3 million, like we did above, is going to go into our denominator since that's the total number of jumps that we had. And then this time, since it's not dying, we're going to put in the value of number of people that did not die while making a skydiving jump, which we just calculated, and then dividing this out, and we get 0.999993. So very likely of not dying. Right below this, there's a little formula, which is the probability of a complement of an event. And so the probability of A bar is equal to 1 minus the probability of A. So the example right below says the probability of owning a 4-bedroom house is 0.183. What is the probability of not owning a 4-bedroom house? So the probability of not owning a 4-bedroom home is equal to, and using that formula that is given up above, 1 minus the probability of owning a 4-bedroom home, which is 0.183. So subtracting this on your calculator, we get an answer of 0.817. So this is the probability of not owning a 4-bedroom home. Right below, it says, if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we would typically expect, with any assumption, we can conclude that the assumption is probably not correct. So we have these words that we saw before, which is that something is significantly high or significantly low. And so for this would be for significantly high number of successes, we're at the probability of X or more. And then the second one says a low number of successes is going to be the probability of X or less. But for both of these, significantly high and significantly low are going to be things that just don't have a likelihood of occurring. This means that we have a very small probability of them actually occurring. And for us, having something small is going to mean less than 0.05. So both of these would be less than or equal to 0.05, so very unlikely that they occur. The next section is 4.2, which is the addition rule, multiplication rule, and conditional probabilities. This section discusses the probability that event A or B occurs, or the probability that event A and event B occur. In the previous section, we only considered simple events, but in this section, we are going to consider compound events. So what is a compound event? This is going to be an event that combines 2 or more simple events. On the next page at the top, there's some Venn diagrams, and normally we see Venn diagrams in a history class or a language arts class, and this is a math class, so a little different. So the word and means both, and you can see that on here since that's where both of those circles are occurring, where the overlap is. And then with the word or, this means either or both. And so you can see it's where just A occurs or just B occurs or where they both occur. And so the example right below says a paint store has 9 different colors of paint: yellow, blue, red, green, orange, pink, white, tan, and lavender. Let event 1 be selecting blue, red, white, and pink, and event 2 be selecting blue, yellow, white, green, and tan. So part A says to draw a Venn diagram for the paint colors. So there's 2 different events, but if you look at those 2 different events that we have, you'll notice that both of them contain blue and white. And so there is some overlap going on. And so what I drew right now is my rectangle, and this is going to be where I put all the colors in. And I'm going to draw my 2 circles because there's 2 events, and there's going to have an overlap. I'm going to label this number 1 for event number 1 and number 2 for event number 2. So we're going to start with what they have in common, and that was blue and white. All the colors that I gave all start with a different letter, and so I'm going to just write the letter that they start with to symbolize that color. So I'm going to put a B and a W in the center part where there's the overlap. So now event 1 is selecting blue, red, white, and pink, but I already have in that circle for event 1, I already have blue and white in there. So that means I just need to add red and pink. And it goes inside circle for event 1, but not in the overlap part. Likewise for event 2, if you look at event 2, you already have blue and white in that circle. And so we just need to add yellow, green, and tan. So yellow, green, and tan. And so this represents all the colors for event 1 and event 2. Now we need to look at the colors, and was there any colors that we had that were not accounted for in event 1 or event 2? And you'll notice that lavender is not in either of those events. And likewise also orange is not in either of those. So because they're not in event 1 or event 2, they are going to be in my rectangle on the outside but not inside those circles. So lavender and orange. Part A on the right column says find the probability of event 1 occurring. So the probability of event 1 is equal to, and so the total number of colors that we have that we were given is going to be 9. So I'm going to write down n is equal to 9. And the number of colors that we have for event 1 is 4. So we're going to have 4 divided by 9. I'm going to leave these as fractions this time, but normally we represent our probabilities as decimals. But now for part B, it says find the probability of event 2 occurring. And so if you look at all the colors in event 2, there was 5. So the probability of event 2, there was 5 divided by our total number of colors, which was 9. And then part C says find the probability of event 1 or event 2 occurring. So probability of event 1 or event 2 occurring. And so counting up all of the colors that we have in event 1 and 2, I'm going to go ahead and highlight them as we go. So we had red, pink, blue, white, yellow, green, and tan. So counting those up, we have a total of 7 different colors. And so this is going to equal 7 divided by the total, which is 9. And it says down at the bottom, notice that probability of event 1 plus probability of event 2 does not equal the probability of event 1 or event 2. Notice that white and blue are in both events, but we only count them once, so make sure not to double count those values. So what we just demonstrated right above is the addition rule. And this says for any 2 events, A and B, the probability of A or B is equal to the probability of event A plus the probability of event B minus the probability of A and B. So we don't double count the part that's inside the middle, that blue and that white. So the example right below, we're given a table, and it says a guidance counselor at a middle school collected the following information regarding the employment status of married couples within the school boundaries. So you can see who worked, either the husband only, wife only, both spouses, and then the total was given. And then also is the number of children under 18 years old. So we either have no children, one child, two or more, and then total. So part A says, what is the probability that only the husband works or only the wife works? So only the husband works or only the wife works. So probability only H, I'm going to say for husband, or only W for wife working. And so for this problem, we have a total number of people that the data was collected from, and you can see that on your table. It's 1,700. And so with that said, that's going to be the number that goes into the denominator. And what's nice with tables is that you don't really have to use any kind of formulas. You just kind of have to read the table. And so doing that, only the husband works. We have a total of 425. And we got that number by adding up 172, 79, and 174. And then it says, or only the wife works. And the total number of people where only the wife works is 126. And so those two values I need to add together. So we have 425 plus 126. On the calculator, we're going to take 425 plus 126, which is our numerator. I'm going to select enter, and I get 551, and then I'm going to divide this by our denominator, which is 1,700. Enter. And you'll see our decimal. We need to round this correctly 4 decimal places. When you add together the numerator, you get 551 divided by 1,700. Rounding our probability answers typically is going to be 4 decimal places, so we get 0.3241. For part B, it says, what is the probability that for a married couple selected at random, the couple has no children or only the husband works? So the probability of having no kids or only the husband works. So from this, again with the table, it's nice because we're able to highlight. And so with that said, the 1,700 is still our total sample. That's the people that were asked this survey question. And we're going to add up, and I'm going to go ahead and highlight. It says the people with no kids, and so that would be 172, 94, and 522, which is a total of 788. So we have a total down here that was given, plus only the husband works. But notice that that 172 was already accounted for, so I just need to add up 79 and the 174 to that. So I think it's easiest is just adding up these numbers, and I'm going to write them all down, so it's a very long numerator. But we had 172 plus 94 plus 522 plus 79 plus 174. On the graphing calculator, we need to add up everybody who has 0 children or only the husband works. So having no children, we have in the numerator 172 plus 94 plus 522 plus, and then only husband works, we've already accounted for the 172 people. So left over we have 79 plus 174. So we get 1,041 people total. And then we have to divide this by our denominator, which is 1,700. And we get an answer here that we need to correctly round 4 decimal places. We get 0.6124. Right below this, it says contingency tables. These are two-way tables, and it relates categories of data with row variables and column variables. So like this one had number of children under 18 years old, and the other one was who was working in the family. Next thing we have is disjoint event or mutually exclusive. Both of these words get used, so make sure to know both of those vocab words. These two events, A and B, have no outcomes in common, and so because of this, the probability of event A and event B is just going to be 0. It's unlikely, it's impossible for them to both occur if there's no overlap. So we have an example right below that says a store has 6 different equally likely colors of paint. We have yellow, blue, red, green, orange, and pink. It says let event 1 be selecting green and orange paint, and event 2 be selecting pink paint. So this is very similar to the example we did earlier. However, if you notice, this time there is no overlap. So these are mutually exclusive or disjoint events. And so with that said, when I draw my Venn diagram, I'm going to draw my 2 circles, but they're not going to have any overlap. And so I'm going to have event number 1 and event number 2. And event number 1 was selecting green or orange paint. And so I'm going to go ahead and put a G and an O in event 1. Event 2 is selecting pink paint. And then the colors that we were not using for event 1 and event 2 are yellow and blue and red. And so those are going in the rectangle but not inside event 1 or event 2 circles. So part B says find the probability of event 1 occurring. So probability of event 1, there are 2 colors divided by, and the total number of colors that we have is 6. So this works out to be 1/3. You can divide this on your calculator also and get a decimal answer. I'm going to leave it as a fraction this time. And then we have the probability for part C. Find the probability of event 1 or event 2 occurring. So event 1 or event 2 occurring. And so counting up the ones that are in event 1 or event 2, we have green, orange, and pink, which is 3 out of the total, which is 6. This simplifies to 1/2. And I'm going to leave it as a fraction, but you can definitely write it as a decimal also. So the next thing we have is the complementary events and the addition rule. So complement events and the addition rule. So probability of A or A bar is equal to the probability of A plus the probability of A bar minus the probability of A and A bar. And so this is the probability of event and its complement, and this is just going to equal 0. So this formula just simplifies the probability of A plus the probability of the complement of A. The next part that we have is called conditional probability, and this is denoted PF, and there's a straight up and down line, and that straight up and down line stands for the word given. So this is the probability of F given E, and so definitely something we need to know. The probability of F given E is the probability that event F occurs given that E has already occurred. So we have an example here, part A and part B, and it says suppose a single die is rolled. What is, and A says the probability that the die comes up with a 3. So the probability you roll a 3. There's a total of 6 different numbers on a dice, so it's 1, 2, 3, 4, 5, and 6. And that's just one thing that can occur is 3, and that's what we want. So we get a value of 1/6. Whereas for B, it says we are now told the outcome will be an odd number. What is the probability that the die comes up with a 3? So the numbers that we could roll again were 1, 2, 3, 4, 5, and 6, but we are told that it's an odd number. So that means it cannot be 2, cannot be 4, and cannot be 6. So now we're asked to find the probability of rolling a 3, but given some information. We're given that it's an odd number. And so what happens now is that instead of there being a total of 6 different things, we now only have 1, 3, and 5 that it could have landed on. And so this means that the denominator is going to be 3, because there's 3 different numbers that we have to choose from. And rolling a 3, there's only one of those, so 1/3. So it says, notice the conditional probability reduces the size of the sample space, so the denominator got smaller. So smaller denominator, which is your bottom number. So we have a formula for conditional probability. It says if A and B are 2 events, then the probability of B given A is equal to the probability of A and B divided by the probability of A. Or sometimes you are given numbers and not probabilities, and so we have the number of A and B divided by the number of A. So the probability of B given the occurrence of event A is found by dividing the probability of A and B by the probability of A, or dividing the number of outcomes in A and B by the number of outcomes in just A. So we have an example right below that says the following data represents the number of speeding tickets issued to individuals in the past year and the gender of the individuals. Determine the following probabilities based on the result of the survey. So part A says, what is the probability that a randomly selected individual was issued no speeding tickets last year, given the individual is female? So this word given, we know, is that conditional probability. So this is asking for the probability that 0 tickets were issued, so 0 tickets, given, which we use that straight up and down line, the individual identifies as female. And so using the formula that's up above, this is going to be the number of people that have 0 tickets and are female, and female divided by the number of people that are female. So the people that have 0 speeding tickets and are female is 97. So that's going to go in the numerator. And then the number of females that we have total is 115. So we have 97 divided by 115. Using your calculator and rounding 4 decimal places, we get 0.8435. Part B says, what is the probability that a randomly selected individual is female, given the individual has not been issued any tickets in the past year? So no tickets. So the probability that they're female, given that they're issued 0 tickets. So it's very similar idea to what we did up above, but this time if you notice the female and the 0 tickets are pretty much switched. And so in the numerator it's going to be the number of people that are female and have 0 tickets divided by what is given this time, which is number of people that have 0 tickets. And so for this, in the denominator, we are going to have the number of people that have 0 tickets. And 0 tickets, the total that we have is the 168. And then the numerator, it says they're female and they have 0 tickets. And that's that 97 like we saw in the previous part. So 97 divided by the 168. Dividing on our calculator, rounding 4 decimal places, we get 0.5774. Part C says, what is the probability that a randomly selected individual is male, given the individual has been issued only 1 speeding ticket in the past 12 months? So the probability that they are male given 1 ticket. And so again, using the formula up above, it's going to be the number of people that are male and have 1 ticket divided by the number of people, and this is what is given, which is the second thing that you wrote, which is 1 ticket. So above we have the denominator, which is issued 1 ticket, and we know that there's 21 people that were issued 1 ticket. And then how many of them are men that were only issued 1 ticket? And so that would be 7. And so we're going to have 7 over 21. And dividing it out and rounding 4 decimal places, we get 0.3333. The label on a medicine bottle claims that there is a 14% chance of experiencing insomnia. There is a 5% chance of experiencing both headaches and insomnia. What is the probability that a person who takes the medicine has a headache given that they have insomnia? So what's the probability that they have a headache given they have insomnia? And so for this, I'm going to use P's since I don't have numbers. I have probabilities this time, or percentages. And so this is going to be the probability that they have a headache and insomnia divided by the probability of what is given, which is that they have insomnia. And so looking at the numbers given, it says that there is a 14% chance of experiencing insomnia. And so 14% needs to be written as a decimal. And so remember 14, to change our percent to a decimal, we move our decimal point twice to the left. So this is equal to 0.14. And that's going to go in the denominator because this is only talking about insomnia. And likewise, it says there's a 5% chance of experiencing both headaches and insomnia, and that's going to be the numerator that we need. So again, moving your decimal point twice to the left, and that empty space is going to be a 0. And then dividing this out on your calculator and rounding 4 decimal places, we get 0.3571. The next example says the table below shows results from a test on hepatitis C, and it says among HIV infected patients. And so you'll notice that this time the table that's given to us is missing the totals. And a lot of times it's nice to come up with those totals. So in order to get the totals, you just add up the columns and the rows. So the first column is 335 plus the 2 would be 337. The next one would be 10 plus the 1,153, which is 1163. And likewise for the rows, 335 plus 10 is 345. And then 2 plus the 1,153 is 1,155. And so working this out, you can get your totals. And from here, you can get the actual number of people that were surveyed. So part A says find the probability of selecting a subject with a positive test result given that the subject does not have hep C. So it does not have hepatitis C. And it says, why is this problematic? So we'll talk about that in a moment. But first, probability that they have a positive test given they do not have hep C. So no hep C. And so with our conditional probability, the denominator is what's given. And I'm going to use the number symbol since I have numbers this time and not probabilities or percents. And we'll say no hep C is in the bottom. In the top, it's going to be both of those. So it's going to be the number of people that had a positive test and they have no hep C. And so looking at your table up above, the number of people that do not have hep C, so no hep C, total is 1,155. And in the numerator, it says that they have a positive test and no hep C. And we have a total of 2 people that had that result. And so that'd be 2 out of the 1,155 people. So dividing this and rounding 4 decimal places, we get 0.0017. The question on there also says, why is this case problematic for test subjects? And so they got a positive test result even when they did not have hep C. So you'll notice it's just a couple people, but it still would be problematic since that would cause anxiety for that test subject. Part B says find the probability of selecting a subject with a negative test result given that the subject has hepatitis C. So the probability of a negative test result given that they have hep C. And so again, it's going to be the number of people in the denominator that have hep C, which is given. And then in the numerator, it's both of those, negative and hep C. So negative and they have hep C. So this is problematic also, but a different type of problematic, since this time it's the probability that they got a negative test result, but they actually have hepatitis C. So this time the number of people that have hepatitis C is 345. And then in the numerator, it says the number of people that have a negative test result, but they have hep C. There was a total of 10. So our numerator is going to be 10. Denominator would be that 345, which we can divide in round 4 decimal places, and we get 0.0290. So the next thing right below is the multiplication rule. And this is the probability that two events, A and B, both occur. And notice that word and here is going to be the probability of A times the probability of B given A. And then we get into independent and dependent events. So independent events is the probability that one event occurs in no way affects the probability of the other event occurring. Whereas dependent events is the probability that one event occurring influences the likelihood of the other event. So example right below says determine whether events E and F are independent or dependent and justify your answer. So E is a speeding on the freeway and F is being pulled over by a police officer, and we'll say these are dependent. The reason why is because if you were speeding on the freeway, it's most likely why you were getting pulled over. B says E is the event you get a high score on a statistics exam, and F is the event the Dodgers win a baseball game. So these two things have nothing to do with one another, and so these are independent. We have another formula right below at the bottom of the page, and this is the multiplication rule for independent events. It says if A and B are independent, then the probability of A and B is the probability of A times the probability of B. And again, this only works if they are independent, but definitely a formula to know.